In Part 4 of Lecture 2, we will discuss time-sharing systems. Just as multi-programming allows the processor to handle multiple batch jobs at a time, multi-programming can also be used to handle multiple interactive jobs. In this latter case, the technique is referred to as time-sharing because processor time is shared among multiple users. In a time-sharing system, multiple users simultaneously access the system through terminals, with the operating system interleaving the execution of each user program in a short burst or quantum of computation. Thus, if there are n users actively requesting service at one time, each user will only see on the average 1 over n of the effective computer capacity, not counting operating system overhead. However, given the relatively slow human reaction, the response time on a properly designed system should be similar to that on a dedicated computer. Both batch processing and time sharing use multi-programming. The key differences are listed on the slides table. Batch systems will maximize processor time, while time-sharing systems minimize response time. Batch systems will use job control language commands that are read in with the job's program and software, while time-sharing uses commands entered by the user at the terminal. One of the first time-sharing operating systems to be developed was the compatible time-sharing system developed at MIT by a group known as Project MAC, which stood for Machine-Aided Cognition, or Multiple Access Computers. The system was first developed for the IBM 709 in 1961, and later transferred to an IBM 709-4. Compared to later systems, CTSS is primitive. The system ran on a computer with 32,000 36-bit words of main memory, with the resident monitor consuming 5,000 of that. One control was assigned to an interactive user. The user's program and data were loaded into the remaining 27,000 words of main memory. A program was always loaded to start at the location of the 5,000th word. This simplified both monitor and memory management. A system clock generated interrupts at a rate of approximately 1 every 0.2 seconds. At each clock interrupt, the operating system regained control and could assign the processor to another user. This technique is known as time slicing. Thus, at regular intervals, the current user would be preempted and another user loaded in. To preserve the old user program status for later resumption, the old user programs and data were written out to disk before the new programs and data were read in. Subsequently, the old user program code and data were restored in main memory when that program was next given a turn. To minimize disk traffic, user memory was only written out when the incoming program would overwrite it. This principle is illustrated in the figure on the slide. Assume that there are 4 interactive users with the following memory requirements in words. Job 1, 15,000. Job 2, 20,000. Job 3, 5,000. Job 4, 10,000. Initially, the monitor loads job 1 and transfers control to it in figure A. Later, the monitor decides to transfer control to job 2. Because job 2 requires more memory than job 1 must be written out first, and then job 2 can be loaded in, as in figure B. Next, job 3 is loaded in to be run. However, because job 3 is smaller than job 2, a portion of job 2 can remain in memory, reducing disk write time, as in figure C. Later, the monitor decides to transfer control back to job 1. An additional portion of job 2 must be written out when job 1 is loaded back into memory, figure D. When job 4 is loaded, part of job 1 and the portion of job 2 remaining in memory are retained, figure E. At this point, if either job 1 or job 2 is activated, only a partial load will be required. In this example, it is job 2 that runs next. This requires that job 4 and the remaining resident portion of job 1 be written out and that the missing portion of job 2 be read in figure F.